Now we have been saying that we should always use formulas for series and parallel resistances in order to solve the circuit problems as much as we can. Okay, so in order to be able to use the series parallel formula, we have to understand which resistances are in series and which are in parallel. So here is a simple circuit. Now many of you would be able to quickly identify whether resistances R2 and R3 are in series or in parallel. But some of the students might actually become confused. They would say that R2 and R3 are in parallel, whereas they are not. Okay, so they would be completely wrong in saying that these R2 and R3 are in parallel. These two resistances are actually in series. So in this lecture, we would try to devise a method using which we can identify the resistances in series and which resistances are in series and which resistances are in parallel using a very systematic technique. So here is the technique. Okay, so first thing that we do is that we name all the nodes in the circuit. So in this circuit there are only two nodes. Node is a point where the wires in the circuit actually intersect. So at these 2 points A and B, the two wires are intersecting. One is this wire and the second one is this wire. And in the case of A, it is this wire and this wire which are actually intersecting. These are the connection points in the circuit. So we have just named the nodes. For two resistances to be in parallel, they have to be in between the exact same two nodes. So these are the two nodes A and B, and because R1 and R2 are exactly between, are connected exactly across these two nodes A and B, therefore the resistances R1 and R2 are in parallel. In this case, R2 and R3 are not in parallel because they are not connected to the same two nodes. In fact, these two resistances R2 and R3 are in series because the same current I flows through them. So what is the method to identify the resistances if they are in series? The method is you just have to look at the current flowing through each of the resistances. If the same current flows through two or more resistances, then they have to be in series. So R2 and R3 are in series. Now from here on our things become very easy because now we know that this is 2R, this is 4R. So we could simply combine them into a single resistance, which will be 4R plus 2R, which is 6R. Now this resistance of 6R, okay, so these two resistances are gone. Now there is a simple wire here actually. Okay, now this 6R resistance is connected across terminals A and B, and this 3R resistance is also connected across the same terminals A and B. They are same two nodes. Okay, therefore this 3R and 6R are actually in parallel. So now we know how to reduce them. We'll use the parallel formula. So we'll simply write 1 by 3R plus 1 by 6R, and this will become 2 by 6. So this becomes 1 by 3 by 6R. This 3 and 3 cancel. So this becomes actually equal to 2R. So this is the equivalent resistance between these two terminals A and B. So now everything else is gone. We only have a 2R resistance connected here, and of course because the same current is flowing across this resistance R, okay, everything from here on is actually gone. We have reduced it to this resistance 2R. So this R and this 2R are actually connected in series because the same current flows through them and then returns back to back batteries. So same current I is flowing through them. So the equivalent resistance between these two terminals is 2R plus R, which is equal to 3R. So very simple, we were able to solve it. Okay, again we'll use the same technique and try to reduce this problem. We'll do it systematically, okay, because that is what I advise you. Just do it systematically, and once you get used to solving problems, then you can apply all the shortcuts that your heart desires. Okay, so here is again we'll do this. We'll just name the nodes. So here I am naming this node A and this node as B because these two wires here are connecting and these two wires are connecting here. Okay, so I can name these two nodes A and B because two wires are connecting there, and 3 ohm and 1 ohm resistance are actually connected across the exact same two nodes A and B. So for these two resistances are in parallel. Okay, so once we know that these two resistances are in parallel, we can reduce them to a equivalent resistance, which would actually be replace these two resistances. Okay, so this is the equivalent resistance, a single resistance right here, and we call it R. Now this equivalent resistance R, this 2 ohm resistance and this 4 ohm resistance are come out to be in series. So we can simply reduce that, and then the answer would come out to be 27/4. Okay, so you take these two in parallel, 3 ohm and 1 ohm resistance in parallel, that equivalent resistance comes out to be in series with 2 ohm and 4 ohm resistance, because the same current flows through, the current which leaves the battery actually flows through all three of them, and therefore we were able to solve this, and you can also solve it yourself, and the answer will come out to be 27/4 ohms. Okay, you can try solving it yourself, not very difficult. Now here is another very simple example. We'll again do it systematically. We'll just name these nodes as C and D, and because all of these three resistances are between the exact same two nodes C and D, therefore they have to be in parallel, and their equivalent resistance will come out to be R/3. Okay, so now this resistance of R, this R/3 resistance which comes from here, okay, so and then this resistance R are in series because the same current flows through them. Okay, another thing way to check your answer is that whenever I look at the resistances in parallel, the equivalent resistance would come out to be smaller than each of the individual resistance in parallel. So each of the individual resistance in parallel is R/3, my equivalent resistance actually came out to be less than each of those. And then of course this R/3, R and R are in series, so we'll get 2R plus R/3. You can simplify it, this comes out to be 7R/3. That would be the equivalent resistance. Again, very simple, not difficult. Now here is another very simple problem. There are two resistances are connected like this across the same nodes. We'll again try to solve it systematically. Okay, I'm not doing these problems because they are simple problems, they are not trick problems. Okay, we are just doing them to correctly understand the method for identifying which resistances are in parallel and which are in series. So this becomes CD, now this becomes E and F. So these two resistances are in series, are in parallel, they are connected between the same two nodes C and D. So these two resistances come out to be in parallel. If you were to find out their equivalent resistance, this will become 6 will become 12/2, and from here if we simplify it, this will come out to be 12/3. So that is the equivalent resistance across these 2 points. This is 12/3. Similarly, if we were to solve this, then this will come out to be 8/3 ohm. Okay, and again 12/3 and 8/3 are actually smaller than each of the resistances in parallel using which they were formed. So now this 12/3 resistance, this 8/3 resistance, and this 5 ohm resistance are in series. So if you were to, because the same current would actually flow through all of them, so they are in series. If you were to find their value, 12/3 gets simplified to 4, and this is a 5 ohm resistance right here, and then 8/3. You simplify this further, you get 35/3 ohm. That is our equivalent resistance. Very simple, not difficult. Now this, some of you might find this tricky, but again this is not very difficult. It is very simple problem. Here we have a 10 ohm resistance and a 5 ohm resistance. We have to find the equivalent resistance. These two are in parallel, they are connected across the same two nodes. Okay, so we don't even have to name the nodes here. You can do it systematically if you so wish, but we are just going to increase our speed a little bit. So first thing that we do is that we reduce this and we find out the equivalent resistance right here. This would come out to be 10/3. This 10/3 and this 4 ohm resistance are actually in series, so this becomes 10/3 plus 4, so this becomes actually 22/3. So this 22/3 resistance would be connected right here. Now this 22/3 and this 3 ohm resistance are in parallel. Okay, so they are connected across the same two nodes. So we're just going to change the color a little bit. So right here we have this. Okay, so same two nodes, so 22/3 and 3. So their equivalent resistance would come out to be 20. Sorry, we have to invert it as well. So this is 3/22 plus 1/3. Okay, and this will be the equivalent resistance across these two. And then of course this entire thing is connected to this 2 ohm resistance. So why add 2? You can simplify this yourself. This will come out to be 128/3. 31. Okay, very simple, not difficult at all. Okay, provided that we do not confuse ourselves. Okay, so one of the things that you should also remember is that whenever you are finding the resistances in parallel, you just write the entire equivalent resistance in one go. Okay, don't forget this 1 upon. Okay, so whenever I am computing this resistance in parallel, some of the students, what they will do mistake is, for example, this 22 by 3 and 3, what they'll do is that they will invert this 3 by 22 plus 1 by 3, and they'll think that, oh, this is the resistance in parallel, whereas that is not the case. They forget to do the reciprocal once more. Okay, so just write this entire thing, this entire reciprocal thing, 1 upon 3 by 22 plus 1 by 3, write this in one go. Okay, so write this in one go so that you don't forget that I have to take the reciprocal of the answer. Okay, so whenever you are doing the resistances in parallel, you should always remember this. Okay, and this is what we got here, and then of course we have to add +2 because that entire thing is connected to a 2 ohm resistance in series. Okay, so that is again, now this some of you might find this tricky, but of course it is not if we were to approach this problem systematically. Here we have already been given the two nodes A and B. Okay, now think about it this way: which resistances are connected across these two nodes A and B, exactly between these two nodes. So two of them we can quickly identify. One is this 10 ohm resistance and one is this 5 ohm resistance. Another thing to notice is that across this A and B, this entire wire is connected. Okay, so therefore this is another resistance which is connected across the same two terminals A and B. Of course, that one resistance is composed of two smaller resistances. One is 5 ohm and one is 20 ohm, which we will just simplify out right away, and we will just say that, okay, this is our one resistance which is just 25 ohm. Okay, so very simple. Okay, just by identifying the terminals correctly, we were able to quickly get that just by identifying the A and B terminals. Okay, so now we know that our this 1 by this 10 ohm resistance, this 5 ohm resistance and this 25 ohm resistance are connected in parallel. So what would be their equivalent resistance? Again, we write the entire formula in one go so as to not to forget inverting it or doing the reciprocal of the addition. So this will be 1 by 10 plus 1 by 5 plus 1 by 25. Okay, now this entire thing is connected across this one. This will be, okay, plus 10. Okay, so if you can't see how we got this plus 10, just bear with. Let's just simplify this parallel resistance for once, and this will become 1 by 1 by, and of course the LCM of this comes out to be 50. So this becomes 5 plus 10 plus 2, and this 50 we go to the top. So we have here 50 divided by, this will come out to be 17. Okay, so that is the equivalent resistance across here. Okay, so I'll just write it like this. Okay, so this is the resistance we got right there. Okay, and this is the value. Sorry, there is a single resistance. And what is the value of this resistance? This resistance is 50 by 17 ohm. Okay, now the thing to note here is that all of this rest of the circuit is actually gone. We have just simplified it. Okay, so this is also gone, and now we are left with only this much circuit. So there is a 10 ohm resistance, and then there is this our new resistance which is 50 by 17 ohm, and the circuit just ends there. Okay, and these are our original terminals A and B. Now we know that the same current is actually flowing through this 50 by 17 ohm resistance and the 10 ohm resistance, these two resistances. So they are in actually series. So we can simplify this further. So this becomes 10 plus 50 by 17, and this comes out to be 170 plus 50 becomes 220 by 17 ohm. Okay, so that is the equivalent resistance. So we have found out the resistance, but we actually need to find out the current through the battery. So current through the battery, we already know what is the formula for that. No, it's not very difficult. We already know that. So I is equal to V by R. So this becomes 25 divided by R is 220 by 17, and this would be in amperes. If you simplify this, this comes out to be 85 by 44 ampere. Okay, so again, very simple. Okay, so the main thing here was to identify the two terminals A and B and which branches of the circuit, which wires were connected across A and B, and to simplify accordingly. So hope this class was useful. We will be bringing many more circuit. We will be doing analysis of many more circuits, because this is a very scoring questions, and you can expect a couple on these actually in your exam. So definitely very important topic, very scoring. You should be able to answer these questions in less than 60 seconds. So you'll gain some time there, and also you'll be able to do this correctly. So you'll get some marks as well. Okay, thank you very much.